All right, pre-calc students, we've got Unit 4B, Day 9. Today we're going to talk about working backwards. So what do I mean by working backwards? If you read the first question at the start of the notes here, you will know exactly what I'm talking about. And we're pretty close to the end here, guys. We got a little bit of working backwards today, and then maybe one more new lesson tomorrow. And then we're wrapping up Unit 4B on higher order polynomials. So if I gave you the roots and I ask you what's the equation, that's backwards from a lot of what we've been doing lately. Usually I give you the equation and our goal is to find the roots. So if I tell you the roots, we're going to do a little bit of process where we work backwards to determine the equation. And I think you're going to be pretty good at this because if we have roots at -3 and 5, we can think about what factors give me those roots and then multiply them together to get the end equation. So a root at -3 would come from the factor x plus 3. And a root at 5 would come from a factor of x minus 5 when set to 0. And by the way, if I want an equation, it better be set to something. I'm going to choose equals 0 just because when I set this to 0, I get x equals -3 and I get x equals 5. So then we're just going to go ahead and multiply this out, whether it's box method or FOIL, it's up to you. I'll do some quick foiling to get x squared. Outside is -5x, inside's +3x. Minus 15 equals 0. Combine those terms in the middle to get x squared minus 2x minus 15 equals 0. And of course, we can go to the calculator right now and we can double check that it crosses at -3 and 5. We could hopefully factor that again and get back to where I just was a second ago. That equation of this quadratic right here gives you roots at -3 and 5. So what about if the roots are 4 and -1? Is the process going to look all that different if I change the roots to 4 and -1? Absolutely not. You're going to get a factor of x minus 4 to give you a root at x equals 4. You'll have a factor of x plus 1 to give you a root at -1. And as long as I set that equal to 0 to make it an equation, we know that this gives us roots at 4 and -1. So if we multiply them out, we're going to get x squared. Maybe I'll do this step in my head. You get plus 1x, but minus 4x in the middle. So that's a total of -3x minus 4 is equal to 0. And although this is pretty easy for quadratics, it's been easy because of a couple things. We only have 2 roots, so think about what that would look like for 3 and 4 roots and beyond. And then the other thing is that they've been nice integers that we've started with so far. We know that the roots don't always turn out to be such nice looking numbers. So what we're going to talk about is that there is another pattern that might be useful. And that other way that I'm going to show you is dealing with the sum and the product of the roots. So this might be something that you learned last year in Algebra 2 or Algebra 2 Honors. If you don't quite remember it, here's what's going on. From example 1, when the roots were -3 and 5, if you find the sum of the roots, -3 plus 5, that equals 2. If you find the product of those numbers, -3 times 5, oops, that's supposed to be a 5. There we go. We get -15. So go and look at the original equation that we got after multiplying those factors together. X squared minus 2x minus 15. Look at the sum and product. Look at the equation. That's interesting. All right, well, let's see what it looks like for example 2 that we just did. If the roots were 4 and -1 right here, let's find the sum. 4 plus -1 is 3. And the product, 4 times -1 is -4. Look at what the equation turned out to be. X squared minus 3x minus 4. Okay, those numbers look very familiar to me. So check out where the sum and product live in the equation. Sum, product. However, maybe what you're noticing in this case is that, wait, the sum is 2, but this was a -2. The product was -15, and that does exactly match this number here. Here the sum is 3, but that's -3. Product of -4, that stays at the end. So what I want you guys to connect here is the general pattern for a quadratic would be x squared. We're going to change the sign for the sum of the roots, and that would get multiplied by x. and you're going to keep the sign of the product of the roots. And that becomes your C value. That becomes your constant term at the end. Okay? So using that general pattern, let's give us roots that maybe are a little bit more complicated. Like for practice, if the roots are 3 and -1/3, what's the equation? Well, if we find the sum and product, we'll know exactly where to plug those in. So the sum of the roots, 3 plus -1/3. Well, when I add those together, it would really help to have a common denominator. That's how we add fractions. So I'm going to change 3 into 9/3. Plus -1/3 would be a total of 8/3. Okay, so that's a little weird looking, but we'll leave it for now. Sum is going to be 8/3. What's the product in this case? The product would be 3 times -1/3. The nice thing about product is you don't need a common denominator to multiply fractions like we do for adding. So, and in fact, this 3 up here cancels with this 3 down here to get a product of -1. So the way I would write the equation using this general form is x squared. Change the sign of the sum minus the 8/3. That goes next to x. And keep the sign of the product. So keep it -1 equals 0. What you will often see in these questions is that we are required to use integral coefficients. It will say that in directions. It will say, given these roots, write the equation using integral coefficients. What does integral kind of sound like in terms of a number that we know? It should sound like integers to you. So if we have to use integral coefficients, that means that 8/3 is no good because it's not an integer. So how are we going to fix the fact that 8/3 is not an integer? You're going to multiply both sides by the LCD, which in this case happens to be 3. If you have multiple fractions here, you'd multiply by the LCD of both. But it's pretty easy to just, hey, distribute a 3 here to get 3x squared. Now the middle term is minus just 8x. And then -3 at the end equals, well, nice thing about this is that 0 times 3 keeps that a 0 at the end. That's the equation I'd want to see as your final answer. So definitely a step up in level of difficulty when you have some fractions in the mix, but we'll get more practice where we have to deal with those integer coefficients. All right, so what if the roots are 1 plus or minus radical 3? If these are the roots. Well, first and foremost, maybe think of them as being separate, right? It's 1 plus radical 3 and 1 minus radical 3. So let's talk about the sum. The nice thing is that when you find the sum, the radicals cancel. So you get 1 plus 1, which is 2. In thinking about the product, you might just have to carefully do box method or FOIL. I'm not a big box methoder, guys, so I'm just going to do some FOIL quick. We get 1 times 1 is 1. The outside is negative radical 3. The inside's positive radical 3. You'd get the same thing with box, right? Minus radical 3 times radical 3, which is 3. And notice how those radical 3 terms cancel. You're left with 1 minus 3, which is -2 for the product. You will never write an example of a quadratic equation that has radical coefficients. That's just not going to happen. So you'll always find that these radicals kind of go away when you do the sum and product there. So what's the answer in the end? Well, it's x squared. Change the sign of the sum, right? Change the sum. So minus 2x, but then keep that product -2. Don't forget about equals 0, okay? And by the way, those were irrational roots, right? 1 plus or minus radical 3. They're not complex. How do we get complex roots? Something like, what if the roots are plus or minus 2i? So we definitely have 2 roots. One is 2i, one's -2i. The sum of the roots, 2i plus -2i, is sum of 0. That's weird. All right, what about the product? The product would be 2i times -2i, which is -4i squared. Oh, by the way, just like your quadratic will never have I or radicals as coefficients, it will never have i's either. Because we know that I squared is -1, don't we? Well, at least I hope we do. -4 times -1 is 4. So to write the equation of a quadratic whose sum is 0 and product is 4, it's going to be x squared. Technically, I guess like minus 0x, even though we typically wouldn't write that if the coefficient of x is 0. Keep the sign of the product, so plus 4 equals 0. And I can confirm so fast that the roots are plus or minus 2i by subtracting 4, square root, square root. You're going to get those same two roots, so that definitely should be making some sense to us. Okay, so we've gotten some good solid practice with quadratics, but of course, where are we headed with this? We can extend it for cubics. So what we're going to see is that if we had some time to develop this, we can figure out the equation for cubics, and it's still dependent on knowing sum and product. But since cubics have an extra coefficient, because it has 4 terms instead of 3, there's going to be one new piece that we have to add onto the process. So for a cubic polynomial, it's going to start off with x cubed. You're going to change the sign of the sum, and that's going to now be the coefficient of x squared. Just like I was changing the sum and that went next to x before, now the opposite sign of the sum is the coefficient of x squared. Then for the x term, this is the new coefficient. It's the sum of the product of the roots when taken 2 at a time. And that's probably very confusing to you right now. I promise we'll make some sense of it in 1 second. It's the sum of the products taken 2 at a time. That goes next to x. And then at the end, it's going to be minus the product. Don't forget about equals 0. Remember a second ago for quadratics, we kept the sign of the product. For cubics, it will always be the opposite sign of the product. Because what happens is we're going to keep x cubed the same. We're going to keep it positive out front. You're going to change the sign of the sum. You're going to keep the sign of this new coefficient, sum of the products 2 at a time, and then you'll change the product. So the signs will alternate throughout, that you keep the first term always, change, keep, change as we go down the line. And this product will eventually, or this pattern will eventually get extended to other examples. Okay. So taking a look at something, let's pick nice roots to start, just to kind of get our bearings here. If the roots are 2, 3, and 4, and I said, hey, what's the equation given those roots? In order to do that, these are the 3 coefficients I want to figure out: the sum 2 at a time, and the product. Well, sum's going to be pretty easy. 2 plus 3 plus 4 is a total in this case of 9. So we've got that under control. The product's going to be pretty easy for us as well. I'm just going to multiply all those 3, but let's move on to the sum of the products 2 at a time, which I usually abbreviate as sum 2. Okay, so with a little kind of subscript there of 2. What does the sum of the products 2 at a time mean? It means we're going to take the roots 2 at a time. So like 2 and 3, 3 and 4, 2 and 4. We're going to find the products of those and then eventually find the sum of that list. So let me show you what I mean. We're going to take the 2 and the 3, pair those up, find their product. Then maybe I'll pair up the 2 and the 4. That's another pair I can make with the roots. The only other pair that I haven't done yet is pair up the 3 and the 4. Whatever those products are, we're going to find the sum of the products when the roots are taken 2 at a time. So this would be 6, 8, and 12. And if you add those 3 numbers together, that's going to wind up being the coefficient that we put next to x. So that's 26. It's the sum of the products of the roots when taken 2 at a time. Finally, the product of the roots, all 3 at once. 2 times 3 times 4. So those 2 would multiply to 6 times the 4 at the end is 24. And now that I have each of these terms, I'm just going to very carefully sub them into this general form and be able to come up with the equation for this cubic polynomial. So here we go. Ready? It's going to be x cubed. change the sum, minus 9x squared. Keep the sum 2 at a time, plus 26x. Change the product to minus 24 equals 0. That's the equation of a cubic that has these 3 roots. Okay. Takes a little while to get used to this new pattern, just like anything, but I know that with some more practice we'll get there. So if I said that the roots are 2 and 1 plus I. 2 and 1 plus I. Well, if 1 plus I is root, here's what's tricky. It looks like there's only 2 roots currently. So you might think, oh, it's quadratic. But is 1 plus I ever a standalone root by itself? The answer is no. These come in pairs, conjugate pairs. So if 1 plus I is a root, so is 1 minus I. Quick little sneeze in there for you guys. Okay, so we have 1 plus I, and again, you're just going to write 1 minus I if that's not listed. Sometimes we get a little sneaky with that. And it's not going to be that much more challenging when you have complex roots. I think the numbers are going to be smaller than this last case here. So what's the sum? 2, 1 plus I, and 1 minus I. Add them up. I'm getting 4, right? 2 plus 1 plus 1. I's are going to cancel. Let's talk about that sum 2 at a time and what that looks like. We got to think about finding products of pairs of roots. We're going to take the products 2 at a time and then find that sum. So 2 is going to get multiplied by 1 plus I. 2 is going to get multiplied by 1 minus I. And the last pair is 1 plus I times 1 minus I. Here's the roots 2 at a time. We're going to find the sum of those products 2 at a time. 2 times 1 plus I is 2 plus 2i. 2 times 1 minus I, 2 minus 2i. Those are pretty easy, right? We're just distributing. But 1 plus I times 1 minus I, you got to be careful about that. Maybe I'll give a shout out to my box methoders of the world. 1 plus I, 1 minus I. Okay, conjugate pairs, nice things happen there. Terms will cancel, but you do have to be cautious about what I'm left with here, right? So notice how when I do the box method, negative I and positive I cancel. You're left with 1 minus I squared. But oh wait, I squared is negative 1. Which turns into 1 plus 1, better known as 2. It's really easy to lose track of some of that there, so be careful about this. But you got to make I squared into negative 1 such that then we get that that product is 2. When I add all these up, because we're finding the sum of those products 2 at a time, 2 plus 2 plus 2 is 6. Okay. And here's the great thing about now doing the product. The product is all 3 of them at once, 2, 1 plus I, and 1 minus I. We've already done the hard work. We already know what this product is because we just did it over here. 1 plus I times 1 minus I is 2. So you use that to your advantage to get 2 times 2, which is 4. And we've got the sum 2 at a time, and the product. So my final answer is x cubed minus 4x squared. Change the sum, right? Keep the sum 2 at a time, plus 6x. Change the product, equals 0. We're done. Okay. At this point, we probably benefit maybe just from one more real quick, so stick with me for one more here. And then I promise we'll do some practice next time I see you in class. If the roots are negative 1 and then 3 plus or minus the square root of 2. We'll go back to having some irrational roots here. All right, so let's talk about the sum. Negative 1, 3 plus radical 2, and 3 minus radical 2. Add them up. Radical 2's go away. They have to. 3 plus 3 is 6. Minus the 1 up there is 5 for the sum. Sum 2 at a time. Are you getting any more comfortable with this, I hope? Take negative 1, multiply it by 3 plus radical 2. Take negative 1, multiply by 3 minus radical 2. And then the last one is that conjugate pair, 3 plus radical 2 times 3 minus radical 2. Okay, so for the sum 2 at a time, distribute negative 3 minus radical 2, negative 3 plus radical 2. Okay, distribute those negative ones. And then from there, if I multiply those together, Since they're a conjugate pair, you'll find that the outside-inside products cancel all the time. So for those of you who are box methoders, these two are going to cancel out. So you're just left with 3 times 3, which is 9. Radical 2 times negative radical 2, which is a negative 2. So be careful about that. But radical 2 times radical 2 is 2. It's negative. 9 minus 2 is 7. You'll get that from FOIL, from box method, whatever you want. Okay, radical 2's cancel. Negative 6 plus 7 is 1 for the sum 2 at a time. And finally, the product, the grand finale here. Negative 1 times 3 plus radical 2 times 3 minus radical 2. Well, we've already determined that this thing is 7. We just did that a second ago. 7 times negative 1 is negative 7. So with all these pieces put together, it is x cubed. Change the sum, minus 5x squared. Keep the sum 2 at a time, plus 1x. Change the product to plus 7 equals 0. Done. Okay? We will do a lot more practice, I promise. We'll even extend this process a little bit further in our last lesson tomorrow. Have a great rest of your day.